Hello everyone, welcome to our new episode. In this episode we're going to talk about mixed strategy Nash equilibrium. It's not a new concept, it's just we apply the idea of Nash equilibrium in mixed strategies. Alright, so why do we do this? Why do we need this? The reason is simple, because not all games have Nash equilibrium in pure strategies. The matching pennies is one example. So remember, there are two players. Each player has two strategies, either head or tail. And if the players simultaneously and independently choose their strategies, once they, after they choose their strategies, if their choices match, head or tail, player one wins, player two loses, and so assume that player two pays $1 to player one. Otherwise, player two wins, player one loses, so that means player one pays $1 to player two. All right, so in this game, let's try to find the Nash equilibrium strategies, Nash equilibrium in pure strategies. All right, so what does that mean? Let's calculate the best responses. So if the second player plays head, what is the best response for the first player? Well, clearly head, because +1 is higher than -1. So I underline +1 indicating that head is the best response to head. Well, what if player 2 plays tail instead? Well, in this case, tail is the best response because +1 is higher than -1. Okay, well, what about player 2's best responses? So let's suppose player 1 plays head. What is the best response for player 2? Is it head or is it tail? Well, clearly tail, because +1 is higher. And what if player 1 selects strategy tail? In this case, the best response is not tail, it's head. So I underline +1. So what does that mean? That means, in each entry, there's only one number that is underlined. That means, for example, for this strategy profile, player 1 is best responding player 2. However, player 2 is not best responding player 1. So therefore, HH is not a Nash equilibrium. Similarly, with exactly the same reasoning, tail, or head, tail, or tail, head. So those four four pure strategy profiles, and none of them are Nash equilibrium, because either only one player best responds the other, but it's not the case that both players are best responding. Put differently, if one of those outcomes realized, one of the players is going to regret his or her choice. All right? So that means in this game, there's no Nash equilibrium in pure strategies. But again, we would like to come up with a theory, a solution concept that recommends something, some outcome, some potential outcome in every possible reasonable games. And this is quite a reasonable game because it's finite, simple two-person game and with two strategies. So one way of dealing with this type of problems is to extend the idea of strategies without changing the game structure. So what does that mean? That means, well, what if the players are not allowed to choose a strategy from S1, S2, which is head, tail, right? These are pure strategies. But instead, we let them choose from this set, delta S1, delta S2, which is basically a simplex. Remember the definition of mixed strategies. So it's basically some probability distribution, P1 minus P. So P is the probability of head, 1 minus P is therefore probability of tail, because there are two pure strategies. Any mixed strategy is going to look something like this, P1 minus P, such that P is in 0-1 interval. All right? So therefore, this is what a mixed strategy, the set of mixed strategies will look like. And so we basically ask the same question. Well, yes, there is no Nash equilibrium when we restrict our attention to those strategy sets. But what if we enlarge the idea of strategy to mixed strategies? Then can we find Nash equilibrium? Meaning a profile, sigma 1, sigma 2. Sigma 1 is, for example, I'm just giving an example. With 1/3 probability, player 1 is going to play head. with 2/3 probability he's going to play tail, and player 2, she's going to play with 1/4 probability head and 3/4 probability tail. For example, is this a Nash equilibrium? What does that mean? Well, what does that mean in mixed strategies? We just extend the idea of Nash equilibrium in mixed strategies. How do we do that? Well, let's do it more formally. So here I'm going to give the definition. So consider a strategy profile sigma, and remember it's basically a vector of strategies for each player. So n is some number greater than or equal to 2, where each sigma I is coming from this delta Si set, which is a simplex for each player I. Okay, well the profile, this profile, sigma, is called a mixed strategy Nash equilibrium. All right, so in brief, I'm just going to write NE. It always means a Nash equilibrium if and only if the payoff of player I, when he plays sigma I, given that his opponents are playing according to this strategy profile, this payoff must be greater than or equal to his payoff when he plays something else, Si prime sigma minus I, but don't forget the others are still playing the same strategy profile for all Si prime in Si and each player I. All right, so that's it. Well, basically what I'm saying is that the sigma I is a best response for player I to sigma minus I, and this is true for each I. This is exactly the same definition for the Nash equilibrium in pure strategies. Here, the only difference is that this, I don't have Si, but I have sigma I. All right, well, maybe it's important to underline this thing. You may say, why don't I write this definition, at least this inequality as such? Ui sigma minus I, greater than or equal to Ui sigma I prime sigma minus I for all sigma prime in delta Si. All right, well, that inequality clearly, so you see what I mean? So here what I'm saying is once I fix the other, let's fix player I, all right? I have to do this for every player, right? Because I have to check that profile. In this profile, each player is best responding his or her opponent. So fix player I, all right? And then fix his opponent's strategy. All right, then I'm going to compare two payoffs. On the one hand, I have the payoff of the player I when he plays sigma I, which is what's prescribed in this strategy profile. On the other hand, on the other side of this inequality, I have some strategy, but this is, as you see, Si prime. So it's a pure strategy. So the question is this mixed strategy gives player I the highest payoff in comparison to all the other pure strategies he could select it, or he could select? Well, alternatively, you can say the same or similar, not same, similar comparison, but this time I'm asking the question, is sigma I giving player I the highest payoff in comparison to every other pure and mixed strategies available to player I? Well, so clearly here I am making more comparisons, right? Because all pure strategies are also mixed strategies, but not all mixed strategies are pure. For example, this is a mixed strategy, and clearly it's not a pure strategy. For example, the following mixed strategy where player 1 plays head with probability 1 and tail with probability 0. So 1, 0. Or 0, 1, meaning he plays tail with probability 1. So these are actually just another way of representing a pure strategy where player 1 plays head, right? So therefore, every pure strategy is a mixed strategy. So therefore, all of those comparisons are already included here. However, there are a bunch of other comparisons here which are not, which we're not operating here. So the question is, are these two definitions, I mean, I'll just plug this here. Would this give me exactly the same definition? The answer is, I'm not going to formally prove it, but the answer is yes, it is true, meaning whether you use this comparison or this comparison, it makes no difference. And the reason, well, I mean, it may not sort of obvious to you, but here is the intuition. Look, if this payoff is greater than or equal to all the other payoffs, all the payoffs of all the other pure strategies, well then this payoff must be greater than or equal to all the payoffs, payoffs from all the other mixed strategies. Why is that so? Mixed strategies are a convex combination of pure strategies. Therefore, a mixed strategy payoff has to be a convex combination of the pure strategy payoffs. So that means if sigma I is beating all my pure strategy payoffs, well, that means this payoff must be beating the convex combination, the average of all those pure strategies. You see what I mean? So therefore, this payoff must be beating, all the payoffs of all the mixed strategies. Again, if it is not perfectly clear, just fine. I mean, I just wanted to give you the sort of the intuition why they're equivalent. But the reason, I mean, some textbooks use this notation, some textbooks use this notation. I think that's easier. This one is easier to work with. Why is that? Well, because it says you don't really have to make this comparison infinitely many times, because remember, there are infinitely many mixed strategies here. All you have to do is just make this comparison twice. Here, for example, there are two pure strategies, right? So that means you have to compare this expected payoff with this expected payoff under player 1 plays head versus if I is equal to 1 under player 1 plays tail, because there are only two pure strategies. All right, so you have to do this comparison twice. But if that was a mixed strategy, you had to do it like infinitely many times, which is not possible, So therefore, this is much more feasible, and so therefore easier. Okay, so that's it basically. As I said, mixed strategy Nash equilibrium is nothing but the Nash equilibrium, where the strategies are in mixed form. Okay, so let's solve an example. All right, the matching pennies. So how do we find the Nash equilibrium in mixed strategies? Well, I mean, simple. What we do, we find the best response of each player. How do we do that? Well, remember, a strategy for player 1 is going to look something like this. He's going to play head with probability P, and he's going to play tail, therefore, with the remaining probability 1 minus P, because there are two strategies. If I had 3 strategies, then I would have P1, P2, 1 minus P1 minus P2, okay? And similarly, if player 2 plays head, let's suppose player 2 plays head with probability Q, let's use a different letter, and therefore she's going to play tail with probability, 1 minus Q, all right? So therefore, a mixed strategy Nash equilibrium, sigma, has the following form: P1 minus P and Q1 minus Q. So once again, that refers to player 1, first player, and this refers to the second player strategy. So that's basically sigma 1, that's sigma 2. And this P refers to the probability of playing head, probability of playing tail. Same for the second player, probability of playing head, probability of playing tail. So therefore, I need to find the exact value of these P's and Q's, all right? So what is P, what is Q? Don't forget P's and Q's are a number between 0 and 1 because they are probabilities. They can't be less than 0, they can't be more than 1. So, but what exactly? So here's what we do. We find, again, the expected, the best response. So finding best response for player 1. Let's start with player 1. All right, so how do we do that? Well, first, I'm going to calculate the utility, the expected payoff of player 1 when he plays H and when his opponent plays sigma 2. So here, the sigma 2, I mean Q1 minus Q. All right, so when player 1 plays head, he's going to get +1 with probability Q, right? Because his opponent is playing a mixed strategy. Or let's assume, I mean, it's not a strategy, but it's a belief. So what belief is going to constitute a Nash equilibrium, all right? So here, player 1 believes that his opponent is going to play head with probability Q, so therefore he's going to get +1 with probability Q and -1 with probability 1 minus Q. So it's +1 probability Q minus 1 probability 1 minus Q. If you just sum them up, you're going to get 2Q minus 1. All right? What about, it's the same player. So what about the payoff of the first player when he plays tail instead? Still, I'm keeping the second player's strategy as sigma 2, which is Q1 minus Q. Well, again, this time it's -1 with probability Q and +1 with probability 1 minus Q. So it's -1 Q plus +1, 1 minus Q. So if you make this calculation, what you're going to see, it's equal to 1 minus 2Q. All right. Okay, so which one is the best response to Q, right? Well, if U1H sigma 2 is greater than U1H, tail sigma 2, well then that means playing head gives higher, strictly higher payoff than playing tail. So therefore head is the best response. Head is a best response. Well, what does head correspond? So playing head meaning playing head with probability 1, right? I mean, you are not going to play tail because head is definitely better. So head is the best response means playing head with probability 1 is the best response. That means P is equal to 1 is the best response. Okay, be careful about this. Well, however, if payoff of playing head is strictly less than payoff of playing tail, well then, as you see in these sort of comparisons, remember, I am keeping the other player's strategy fixed, which is Q, 1 minus Q. So here, this time, tail gives strictly better payoff. So the best response is playing tail for sure, which means P is equal to 0 is the best response. So T is a best response, or equivalently, P equals 0, right? Because tail corresponds P equals 0, so this is probability 1, this is probability 0. Okay, well, what if there's another scenario, a possible scenario? The expected payoff of head is equal to expected payoff of tail. Well, what is in this case? So player 1 gets exactly the same payoff between playing head and tail. So he can play head, so head is the best response. He can play tail, tail is the best response, right? Because they both give exactly the same payoff. But you know what? Any combination of head and tail is also best response, right? Why is that? So if you play head and get payoff 5, and if you play tail and get payoff 5, so whatever mixed strategy you play, for example, you play head 50% of the chance, tail with 50% of the chance. So what's going to be your expected payoff? 5 times 1/2 plus 5 times 1/2, 5 again. Let's say you play head 1/3 of the chance and 2/3 probability you're going to play tail. What's going to be your expected payoff? 5 times 1/3 plus 5 times 2/3. Again, 5. So, therefore, any P in between 0, 1 is best response. Okay? So it's not only head, but also tail, and also all the combinations, all the mixture of head and tail are best response. Okay, that part is probably the most important part of this question, all right? So pause for a minute or 5 and think about it. All right, so what I'm going to do next is I'm going to draw the best response function, all right? Well, it's not a function really, it's a correspondence. So let's put P here, Q here, all right? So these are the strategies of player 1 and player 2, right? Player 1 strategy is P. So here, the best response of player 1 is a function of Q, remember? Okay, so here, what does this inequality means? U1H sigma 2 is greater than U1T sigma 2. It basically means 2Q minus 1 greater than 1 minus 2Q, right? So if you solve this inequality, all right, so this is if and only if. So send Q to the other side. I have 4Q, 1 to the other side, 2. So Q greater than 1/2. So if Q is greater than 1/2, well then P equals 1 is the best response. So let's say this is Q equals 1, this is P equals 1. So my best response functions or sets are going to be in this square. I mean, if it doesn't look like square, I'm sorry, that's my bad. So let's put 1/2 here. Okay, so when Q is greater than 1/2, the exact value doesn't matter as long as it's above 1/2, all right? So as long as Q is in this range, P is equal to B1, all right? So therefore, if you draw this function, it's this, all right? So whenever Q is higher than 1/2, I have P equals 1. Very good. What about this inequality? The payoff, expected payoff of head less than expected payoff of tail. Once again, the expected payoff of head is this. Expected payoff of tail is 1 minus 2Q, which if you simplify it, you're going to have 4Q less than 2, meaning Q strictly less than 2, obviously, right? So if this is greater, this has to be less than. Because it's just I'm changing, reverting the direction of this inequality. So whenever Q less than 1/2, P equals 0 is the best response. So this is where my function is. All right, very good. So it's a kind of an awkward function or graph. Well, what is this? Well, this means this inequality, means 2Q minus 1 equals 1 minus 2Q, right? Again, if you simplify this, obviously it means Q is equal to 1/2. So when Q is equal to 1/2, exactly this point, any P in between 0, 1 is the best response. So it's not a function. It's not just one specific P value. So here, for example, so for any Q, just one specific P value, which was 1. Here, for any Q, it was one specific P value, which was 0. But here, for one specific Q value, any P is possible. So that means all these points are best response. So then this sort of step kind of function is the, again, this is not really a function, but anyway. So this is a correspondence. This is a best response function, let's call it, of player 1, okay? All right, well, what I'm gonna do next is I am going to find the best response of the second player, right? Makes sense? So expected payoff of player 1 when his opponent is playing sigma 1, which means the sigma 1 is P probability head, 1 minus P probability tail. However, player 2 plays head, what's going to be her expected payoff? Well, here, expected payoff of player 2, when she plays head, it's going to be -1 with probability P, right? Because she believes that, well, again, so if the mixed strategies or beliefs is not clear, then calculating those expected payoffs will not be clear. So for that reason, to make that calculation clear, please go back to our previous videos where I talk about beliefs and mixed strategies. It's very, very important, okay? You can't really understand one step without understanding a previous step. Okay, so here, she's going to get -1 with probability P and +1 with probability 1 minus P. So therefore, her expected payoff is going to be -1 times P plus 1 times 1 minus P. So if you add them up, what you're going to get is 1 minus 2P. All right? The payoff of player 2, if, again, her opponent plays sigma 1, and then she, however, plays tail instead, well, this time she's going to get +1 with probability P and -1 with probability 1 minus P. So therefore, it's +1P plus -1 minus P. So if you do the math, if you just sum them up, what you're going to get is 2P minus 1. Very similar to the previous one, right? So but instead of, Q, we have P. So be careful. When we calculate the second player's payoff, her her expected payoff depends on P, which is reasonable because P is the second player's belief, right? So your expected payoff should depend on your beliefs. So that makes sense. It shouldn't depend on Q. Because here I am calculating expected payoff of playing head, a pure action strategy, I'm sorry. All right, so once again, if the expected payoff of playing head is greater than expected payoff of playing tail for the second player, well then, so head is better than tail. So therefore, she's going to play head for sure. Head is best response. Well, what does that mean, playing head for sure? It means playing Q equals 1, all right? All right, is a best response. So let's leave some space. If, however, U2 sigma 1 had less than U2 sigma 1 tail, well then that means tail is a best response, which means Q equals 0 is a best response. And then finally, if U2 sigma 1 head and U2 sigma 1 tail gives exactly the same expected payoff, well, that means she's going to be indifferent between head and tail. Well, in fact, any Q in between 0, 1 is a best response. Exactly the sort of same analogy as the player one's best response calculations. So once again, once I have all this, so what does this inequality tells? The second guy's expected payoff from playing head is 1 minus 2P, greater than her expected payoff of playing tail, 2P minus 1. So that's equivalent to saying P is less than 1/2. All right? So therefore, again, let's suppose this is 1/2. So whenever P is less than 1/2, her best response is Q equals 1. So where's Q equals 1? Here's Q equals, well, let's choose a different color because it's gonna mix up otherwise. So this is Q equals 1 as long as P is less than 0. Well, do I have to rewrite those inequalities again and again? Not really. I know that if this means P is less than 1/2, this should mean P is greater than 1/2, and this should mean P equals 1/2. All right? So whenever P is greater than 1/2, the best response of the second player is 0. Q equals 0. So that means this part. And whenever P is exactly equal to 1/2, all the Q's are best response. Okay? So this I know the symbol does not resonate with good memories, but I mean, it has nothing to do with it. So this is exactly I mean, I hope the colors are clear. I do have red. Maybe I should have tried red. Okay. So this one, okay? So this one is the best response of the second player. All right? So that's it. In a sense. Why? Well, because remember, according to definition of Nash equilibrium, so let me clear some space here. I mean, this is not exactly the definition I gave you, but they're identical. Sigma I has to be best response for player I to sigma minus I for all I, right? So what does that mean? That means sigma 1, sigma 2 is a Nash equilibrium if and only if sigma 1 is a best response to sigma 2, and then sigma 2 is a best response to for player 2 to sigma 1. All right, so that means the point of intersection of these two indifference curves are going to give me the Nash equilibrium, all right? Always. So here, these two best response functions correspond only at one point, which is this, right? Otherwise, they do not cross one another. So that means this point is the only Nash equilibrium of this game. So what does this point correspond to? This point corresponds to P equals 1/2, Q equals 1/2. So I actually found P equals 1/2, Q equals 1/2. This is the Nash equilibrium. If you like, you can write it this way. Sigma 1 is equal to this. 1/2, 1/2. So meaning he's going to play head and tail with equal probabilities. And sigma 2 is going to play 1/2, 1/2. So this is Q, this is 1 minus Q. So this sigma 1, sigma 2 profile is the Nash equilibrium. And the only Nash equilibrium. Again, why only? Again, this is the only point that where the both best responses intersect. All right, so I want to say, so that's it. That's the end of our analysis. And this is exactly how we find the mixed strategy Nash equilibrium. Okay?